Hello, today we're going to take a look at the review for the rational function unit. The first thing we need to do with this one is set our denominators equal to 0 to find what our variable can't be. So in this case, p cannot equal -2. So what we need to do is find our least common denominator and multiply both sides of our equation by it. In this case, it's plus 2. So we have our p plus 2 multiplied by p. Don't multiply anything out because we're just going to factor out anything we can, which should factor out all our denominators. Now, don't forget to multiply the 4 by the p plus 2 as well, because we're multiplying both sides of the equation. It's the only reason we're allowed to do this, and that includes the 4. So in both of these terms, the p plus 2's will factor out. So we're left with p plus, we can distribute the 4. And always remember to do that, especially if it's negative. That's something that people will miss sometimes. Equals 21. We'll combine some like terms. Subtract 8 from both sides. Divide both sides by 5. And get p equal to 13/5. Here, we're taking a look at average speed. Remember, average speed is not the average of the speeds. With all of these problems, whether it's an average speed or looking at rates like going up or downstream, something like that, we're always working off of different variations of this equation where distance is equal to rate times time. So the first 65 miles per hour for the first 100 miles, and then 50 for the final 250 miles, so the nearest mile per hour. Okay, so our average speed, if we take this equation, we divide both sides by time, so it's our total distance divided by our total time. So our total distance is 350 miles. So our total time, we're also manipulating this equation, so time is equal to distance divided by rate. So our time for the first 100 miles is our distance divided by our rate. And then our time for the second 100 miles, remember we're using this, time is equal to distance divided by rate, or the final 250 miles is 50 miles per hour. So what we want to do with this particular case, we want to simplify this term a little. So we have 350 divided by, and we can simplify the 100 divided by 65 as well. We can factor out a 5. So we end up with 20/13 plus 5. So what we need to do is combine these terms. So multiply this 5 by 13/13 to get a common denominator. So 20 plus 65/13. We can now multiply by the reciprocal. So we have 350 multiplied by 13 divided by 85. So we can factor a 5 out of this. So we have 70 times 13 divided by 17. So we end up with whatever this is. Okay, so we have 910/17 miles per hour. All right, taking a look here, the first thing we want to look at is these denominators. So we want to factor these. We've got a difference of perfect squares, 2x plus 2x minus 2. So x can't equal 2 or -2. So our least common denominator is this x squared minus 4, because we're looking for each unique factor in a denominator. So x minus 2 is in all of them, and then x plus 2 is in these. So there are unique ones. So we multiply each of these by x plus 2, x minus 2. Each term, you have to multiply both sides of the equation by it. And here I'm just going to leave it as x squared minus 4 because that's the denominator, and it's going to make it easier to factor out. It's the same thing, just written in a different form. Okay, our x squared minus 4's factor out, our x minus 2's factor out. Now we can distribute this 3. So we have 3x plus 6 plus 5x equals 30. Combine like terms. So we subtracted 6 from both sides, divide both sides by 8, and x is equal to 3. Over here, we've got that x can't equal, you know what, let's switch up the color a little bit. So x can't equal -1 or a positive 2 by setting our denominators equal to 0. Our least common denominator here is x plus 1 times x minus 2. So what we're going to do when we multiply both sides by this, so I'm just going to multiply this out in this step. So I'll have x squared minus x minus 2. So our x plus 1's will factor out. Our x minus 2's will factor out. Now, when we multiply this, so we'll have 5x minus 10. Watch your signs. We've got this negative sign. So it's -7 times x. -7 times 1. Okay. Now, since it's quadratic, we're going to move everything onto the right side. We want to set it equal to 0. So we end up with 8x squared. So this is 5x minus 7x, so it's minus 2x. So we need to add 2x to both sides. So 8x squared minus 6x. We have minus 17. So we'll add 17 to both sides. So plus 1. So here we can then factor this. We know we're going to need a -1 and -1 because both of these, or this sign's positive, so both signs are going to be negative. We want to find our factors of 8x squared. That will add up to 6x then. So by our zero product property, we set each of these equal to 0. So our solutions, we've got x is positive 1/4, and x is a positive 1/2. With something like this, we need to find a common denominator in the numerator and a common denominator in the denominator. So we need to multiply this term by x divided by x and this by 3 divided by 3. Here we need an x squared divided by x squared and multiplied by 3 divided by 3, because in both our numerator and denominator, our common denominator is going to be 3x squared. So our numerator, we end up with x minus 3 divided by 3x squared. Our denominator, we have x squared minus 9 divided by 3x squared. Now we can multiply the numerator by the reciprocal of the denominator. And I'm just going to factor this, this difference of perfect squares. So our 3x squareds factor out, so do our x minus 3, so we are left with 1 divided by x plus 3. All right, so with this, when we are converting this number to a fraction, so our repeating decimals are going to be fractions. So what we want to do is set up an equation. So if x is equal to 1.4 and then 5, 6 repeating, what we want to do is multiply both sides of this equation by 10 because there are two numbers that repeat. So we end up with 10x is equal to 145.6 and then 56 repeating. Then we want to subtract our original number from both sides. We're going to subtract it in the form of x on the left and subtract it in the form of 1.4 and then 56 repeating on the right. It's the same number, just in different forms. So our left-hand side is going to be 9x. Here, what will happen is these repeating decimals will line up going on towards infinity, so they just can subtract away then. So we then just do some subtraction with this. So we have 144.2. We'll divide both sides by 9. But then we can't have a decimal and a fraction, so we need to multiply this by 10 tenths. So that 1.4 and then 56 repeating is the same as 1,442 divided by 90, or you can factor out a 2 from that as well. So taking a look at some previous unit material with limits. So our limit as x approaches -1 from the left, we are going to come from the left as x approaches -1, looking for the y-coordinate. That's going to be 0. So our limit as x approaches 0, that is a two-sided limit. We compare from the right and from the left. Both of those y-coordinates are going to be 0. So our two-sided limit is also equal to 0. So our limit as x approaches 1, that two-sided limit, because our limit to as we approach from the left is 1, limit as we approach from the right is 2. Those are not the same, so our two-sided limit does not exist. Limit as x approaches -1 from the right. So we find -1 on our x-axis. We are taking a look from the right. We know our right from our left, and we look at what that y-coordinate is. That is -1. So as x approaches 2 from the right, we look at that y-coordinate. It's going to be 1. And as we approach 3 from the right, we look at the y-coordinate, and it's going to be -1. Now we take a look at graphing some functions. First thing we want to do is look for our removable discontinuities. So in this case, we can factor out an x minus 1. So it's going to have a removable discontinuity, which looks like a hole in the graph at x equals 1. But the function is going to behave just like x plus 4 divided by x everywhere except at x equals 1. So what we're going to do with this is substitute 1 back into this equation, the new one, like with the x minus 1 factored out. So not f of x, I'm looking for f of 1. So we end up with a removable discontinuity at the point 1, 4. So we find the point 1, 4 on the graph, and we have a removable discontinuity. So then our essential, we set our denominator equal to 0. So in this case, we have a vertical asymptote at x equals 0. So we go on and plot that on our graph. This time we want to compare our exponents. So in this case, we have a horizontal asymptote because our greatest exponent in the numerator and denominator are equal. So if they are equal, we look at a ratio of the coefficients, which in this case is going to be 1. So we've got a horizontal asymptote at y equals 1. For our zeros, we set our numerator equal to 0, so we end up with the point -4, 0. For our y-intercept, we do not have a y-intercept because if we substitute 0 into this equation, we end up dividing by 0. Not okay. So with this function, we have enough information to get a rough sketch of the graph. We know it's going to be close to the asymptote here, intersect this point, and then be close to the asymptote. The same thing's going to happen here. It's going to be close to the asymptote, intersect where it would intersect if we did not have a hole in the graph, and then get close to the asymptote. If you want, you can substitute some more points in and make it a little more precise, but it's going to follow this general pattern with this. Okay, so here we have x squared divided by x plus 4. We take a look at this. We have no removable discontinuities because there's nothing we can factor out. Our essential discontinuities, we have one at x is equal to -4. So we go and plot that on our graph. Now this, since our greatest exponent's in the numerator, we're going to have an oblique asymptote. So our oblique asymptote, we do some long division to find out what our asymptote's going to be, and we care about the quotient. So x squared divided by x is just x, and then we don't care what we have to do another step before we figure out that we don't care about the remainder. So we multiply x by our entire divisor. So we've got x squared plus 4x. We subtract that term. We end up with -4x. -4x divided by x is -4, and we can stop there because we don't care about the remainder. So y is equal to x minus 4 is our oblique asymptote. So we find our y-intercept of -4, and then our slope of 1. And I knew there was one of these problems that year after year I put this on here and the function does not fit on the graph. I can never remember which one it is until it's this one. So we take a look at our zeros by setting our numerator equal to 0. So we're going to get a 0 at 0. And then that conveniently is our y-intercept as well. We intersect the origin. Now, for this one, we need to substitute some other points in. So let's substitute in -5 to see what's going on this interval. So we have -5 squared divided by, what is it, plus 4. So -5 plus 4 is -1. So we have the point -5, -25, which, we can keep going. That's somewhere off the graph. Yeah, just know that it's going to go somewhere in this piece. In between those asymptotes, we know it's going to be somewhere here. So what I want to do is let's substitute in -2, see if we can help us sketch this a little better. So we have -2 squared is 4, -2 plus 4 is 2. So we have this point, -2, 2. Right. So -2, 2. So we know at least it's going to be kind of close to the asymptote, intersect here. Sorry, this is our only 0. So it's going to just like intersect this and then come kind of close to the asymptote. This one's a little off because the scale is larger than this graph can accommodate. So come watch the second part and we'll graph some functions that fit on the graph.